Okay, theories of covalent bonding. Why in the world do we need more theory? Well, the reason we need a theory is because our atomic orbitals, s, p, d orbitals, point spherically or in two lobes or four lobes, but what they don't do is point in the directions of the bonding we've just described with Vesper theory, like trigonal planar or tetrahedral. In order to do that, we need something like this kind of a shape around the central atom, or for the tetrahedral, we need something like that. And so in order to do that, we need some kind of theory. All right, so the first theory we're going to talk about is valence bond theory. And valence bond theory is where you take those atomic orbitals, and we're going to talk about s and p orbitals, and we mix them to form hybrid or mixed orbitals, form hybrids of atomic orbitals. Okay, we're going to talk about that theory in this video, and then in another video we'll talk about molecular orbital theory, which is where the bonding atoms produce entirely new orbitals. And those are molecular orbitals. So instead of combining atomic orbitals to make what you want, you make entirely new orbitals over the entire molecule. Okay, again, we'll talk about valence bond theory in this video. Okay, valence bond theory is also known as VB theory. And again, it's hybrid orbitals, which are mixtures of atomic orbitals. So we're going to talk about mixing first an s with a p, okay, an s orbital with a p, and an s orbital has one orbital. We're talking about a single p orbital. There are three, but we're talking about just one of them. Okay, so these are the atomic, and we combine them to form orbitals that look something like this. Okay, they have one tiny lobe, one big lobe, and we're going to call them simply, since they're mixtures of s and p, we're going to call them sp orbitals. So we create two, okay, and they each have some have one orbital, and those are the hybrids. All right, and so there's two things to note about this. First of all, however many orbitals you started with in atomic orbitals is the same number you created. So there's a conservation of orbitals. Conserved. Okay, you're not going to create more or fewer than you started with. And second, the hybrid orbitals also hold 2 electrons each. Just like the atomic orbitals can hold 2 electrons each, so can the hybrids. All right, so let's try combining others. There's one s and one p. Now let's try combining one s with two p's that are pointing in different directions. Okay, each of those is a single orbital. Okay, so a p in one direction is some value of m sub l. P in another direction is a different m sub l. And when they combine, the three of them can form a shape that looks like trigonal planar. Okay, now each of these is a separate orbital, so I'm no longer going to show the tiny little part of the orbital, only the big part, and that's what these are. So each of these is actually a big lobe with a little lobe. Okay, so each lobe looks like that. All right, and so this makes trigonal planar electron geometry. And we call these, up here they were a combination of one s, one p, so it's called sp. Here we're going to call it sp2, superscript 2, which is a combination of one s and two p's. And since there are 3 of them, we can write 3 orbitals. Started with 3 atomic orbitals, make 3 hybrid orbitals. Okay, we have 3 p orbitals, so let's combine an s, a p, and a p. And together you're going to make 4 orbitals, which will repel and form a tetrahedral shape. All right, and those are going to be called, they're combining S, P, 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 so we call them sp3. All right, let's look at some bonding with these. And we'll use the tetrahedral electron group geometry as our example. And we'll look at hybrids of those orbitals and how they're filled. So we're going to do second row elements looking at the central atom, carbon, nitrogen, and oxygen. And remember that in row 2, which is where carbon, nitrogen, and oxygen are, you have a 2s orbital, and you have the 2p orbitals, 3 of them. Okay, so they're going to combine. Oops. They're going to combine and form sp3 orbitals, all of the same energy. And for all 3 of these cases, we're going to make sp3. And again, there's 4 orbitals because they're combining 3 p's and an s. All right, carbon has 4 electrons in the 2 level, so those 4 electrons will fill 1 in each. Nitrogen has 5, so the 5th one's going to go in one of the orbitals and make 2 in that orbital. Oxygen has 6 valence electrons in the 2 level, so 2 of them will have to pair up in the sp3 hybrids. All right, now let's see what that looks like pictorially around the atom, the central atom. And so we've then created our sp3 hybrids pointing in the shape of a tetrahedron, and remember they're a combination of an s and 3 p's, a px, a py, and a pz to make those. All right, so the carbon has 4 electrons, so 1 goes in each orbital. Nitrogen has 5, 4, and then the 5th one will pair up, has to pair up. Oxygen has 6, 1, 2, 3, 4, 5, 6. 2 of them have to pair up. So in carbon, there are 4 available for bonding that can share. In nitrogen, there are 3, and in oxygen, there are 2. All right, let's see how that looks when you put hydrogens on them. Okay, I'm going to redraw them down here, and then put hydrogen on there. Okay, so there's the one from carbon. A hydrogen comes along, shares its 1s electron, and overlaps orbitals, and that's bonding. On the next orbital, carbon provided 1, hydrogen comes along with its 1s and provides a second electron, and you have bonding. Same thing on all of these. So 1 electron that's shared came from the carbon, 1 from the hydrogen, and they are shared. So we can say we had 4 shared electrons. Nitrogen has only 3 available to share, so it can bond to 3 hydrogens. So we'll redraw that. And nitrogen has 2 that are not paired, and then it can share 3 with hydrogens. And finally, oxygen will have 2 that are shared and 2 that are not shared. Okay, so 2 of the lobes will be completely filled on their own. The other 2 can share with hydrogen, which is why water is H2O and not H3O. All right, and all of these are describing what we call sigma bonds, which are bonds that are directed along the axis between the 2 atoms. So in other words, the bond between nitrogen and hydrogen is between nitrogen and hydrogen. Okay, so we call those sigma bonds. And you will see a different type on the next discussion here. And that's when you have multiple bonds. Okay, so multiple bonds. You have a multiple bond in formaldehyde between carbon and hydrogen. Look at the carbon. It's got 3 electron groups, which means it's got a hybridized 3 orbitals. So that will be S and 2 Ps. So sp2 hybrids. And they will be directed along the trigonal planar geometry. The oxygen is up above, and it will share 2 electrons as a sigma bond, and the hydrogens will look just like they did in the last page. And then you may wonder, well, where are the other 2 electrons? Because carbon has to share another 2 electrons with that oxygen, and where are they? In order to see that, we will do a side view. So the carbon is here with its 3 hybrid orbitals, and then we'll put the oxygen over here with its orbital that's overlapping and sharing as a sigma bond, and outside of the plane, outside of that plane of the molecule, we have unhybridized p orbitals. Okay, since we hybridized sp2, there's another p orbital available that's outside of the plane of the bond, and there's one on the oxygen and there's one on the carbon, and they can interact with their electrons, and that is a known as a pi bond. And the pi bond is not along the bond axis. Here's the sigma bond along the bond axis. This interaction between the p orbitals is not along that axis. It is outside the axis, and that is the pi bond. Okay, and that is made up of pure p orbitals, not hybridized. So you have a sigma bond in addition along the bond axis. All right, let's look at, again, how they combined. You had, in the carbon, you had a 2s and 2p orbitals, and originally you would have the 4 electrons like that. When they hybridize, you make sp2, which is 3 orbitals, okay, from s and p and 2, and you have 3 electrons there, and then you have an unhybridized p orbital where the 4th electron goes. The sp2 are the sigma bonds, the p bonding is the pi bond. All right, let's look at some examples in carbon-carbon bonds. First a single, then a double, then a triple. And this drawing gets a little complicated at this point. So let's look at the hybridization around the carbon. It's 4 electron groups, so it's tetrahedral. The other carbon would have the same thing, so we'll draw that. It would also have tetrahedral. Okay, and then each of those lobes would bond with a hydrogen just like before. Okay, and same thing on the other side. 2 electrons shared. Oops. All right, and 2 between the center. Oops. 2 in the center, and I can't draw them. Okay, there's 2 more electrons in there. Okay, so this is an sp3, and it's a sigma bond. Let's do the double bond case. Okay, in this case, there are 3 electron groups. Up here there was 4 around carbon, but there's 3 around each of the carbons. And so you make 3 hybridized orbitals to do that. Okay, we'll draw the 3, and they form trigonal planar around each. We'll show the bonding ones. We'll put the hydrogens on. They can bond. This is why there's only 2 hydrogens on each carbon, because there's only 2 bonding orbitals available to them instead of 3 above. All right, and this is sp2 hybridization, and that has, in addition, that p orbital that's unhybridized, on each carbon. Okay, and so that interaction I'm drawing with lines, and that is the pi bond. So sp2 is a sigma bond, and you also have one pi bond, which is from the p orbitals. When you have a carbon-carbon triple bond, you have only 2 electron groups, so you're going to get sp hybridization on the carbon, same thing on the other carbon. One on each side, they'll be 180 degrees apart, so you can only put 1 hydrogen on each carbon. And then you have unhybridized p orbitals. You'll have one sticking one way and another set perpendicular to that. And this set will interact, and this set will interact. So you have 1 sigma bond and 2 pi bonds, one from each set of p orbitals. All right, so let's summarize. Whenever you have a double bond, one of them will be a sigma, and that's a hybrid, and it's along the bond axis, just like this one here. And you also have 1 pi bond, not a hybrid or unhybridized, and that is not along the bond axis. If you have a triple bond, you also have 1 sigma bond, which is a hybrid and along the bond axis, and you will have 2 pi bonds that are unhybridized and not along the bond axis. All right, let's have you try some practice. There's 3 examples here. I would suggest you try one, then start the tape and see how you did, and then do the next and the next. Okay, so draw the Lewis structures and count how many pi bonds there are. For nitrogen, you should find that you have to have a triple bond in order to make octets around both the nitrogens. Since it's a triple bond, you're going to have 2 pi bonds. And you will have also 1 sigma in addition. For ammonia, the Lewis structure looks like this. They're all sigma bonds. There's no pi bonds. But in this molecule you have 3 total sigma bonds. All right, in N2O you would have N, N, O, and you'll have double bonds between them. So you have, in each of those 2 bonding positions, you're going to have 1 pi and 1 sigma, which means in the molecule overall, you have 2 pi bonds and 2 sigma. All right, and note that if you did happen to pick a different Lewis structure, such as triple bonding and single bond, which you could have done, whoops, actually I did the dots wrong up here. Let's do it again. I did the dots wrong. I want to make sure this is correct. Okay, and then down here the dots would be 6 around the oxygen. Okay, so if you did pick this one, which actually is less favorable by formal charge, you would still have the same answer. You would still get 1 sigma there, 1 sigma there, and 2 pi's, so you'd get the same thing there. All right, let's summarize some of the recent things we've been saying and assign them to a particular theory. So we're summarizing hybridization and more. All right, and so let's first go with, from each number of electron groups, what the geometry is, and you should actually, I would recommend stopping the tape and filling it out all by yourself as much as you can. But I'll fill it out. Linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. And what are the hybrid orbitals? For linear, it's always sp. For trigonal planar, it's sp2. And for tetrahedral, it's sp3. Some books will talk about hybridization for the next two groups as involving d orbitals, but current theory is that that's not an accurate representation of the orbitals. So I'm not going to cover that. And molecular shape, for linear, it's just linear. For the others, there's more than one choice. Trigonal planar. So these are shapes based on geometries. And the second one is bent. For tetrahedral, you can have tetrahedral. You can have trigonal pyramid. And you can also have bent. So these were the examples of CH4, NH3, and H2O. All right, and then for trigonal bipyramid, you have trigonal bipyramid, you have seesaw, you have T-shape, and you have linear options, all with those groups. And then finally, octahedral. I have to move it down. You have a choice of octahedral shape, or you might have square pyramid, or you might have square planar. All right, and the theories for each of these are, these shapes are Vesper theory. They come out of Vesper theory, and these names also come out of Vesper theory. These hybrid orbitals come out of valence bond theory.